The main topic today is einsteinium, a little-known element. Einsteinium is an artificial element named after one of the world's most prominent physicists, Albert Einstein. Einsteinium is produced in minute quantities, about 1 microgram or 1/1,000,000th of the weight of 1 gram using neutron capture process in isotope production reactors. Today, einsteinium is the heaviest element available to mankind for use in physical and chemical experiments. The heaviest element that exists on Earth is uranium, but einsteinium is the 7th element after uranium in the periodic table. If you want to produce such a heavy element, a lot of neutrons must be added to uranium to make it larger. This would take a tremendous effort. Einsteinium is the kind of element that requires a strong commitment to production. Knowing our intent, a U.S. nuclear institution, the Oak Ridge National Laboratory, offered to produce einsteinium for us as a special case. The fact that we are set to conduct this experiment indicates that this element is very valuable. Japan has obtained einsteinium for the first time, and we are the only laboratory in Japan that can perform this experiment using einsteinium. In addition, no overseas research laboratories have studied or planned similar experiments using this type of accelerator. This is an experiment that only JAEA can perform. JAEA is conducting this experiment using einsteinium for the first time in Japan. This experiment is being performed at 2 facilities. One is a Tandem Accelerator owned by JAEA in Ibaraki, and the other is a large synchrotron radiation facility in Hyogo called Spring 8. The first process of this experiment is being performed using the Tandem Accelerator at the Nuclear Science Research Institute. This process is intended to understand nuclear fission. This process is designed to produce heavy nuclei called fermium. First, an einsteinium target is set up in the apparatus. Then, the einsteinium target is irradiated by a heavy ion beam, such as oxygen, accelerated by the tandem accelerator. The ion bombardment causes a nuclear reaction to produce many different atomic nuclei, including heavy atomic nuclei. In addition to analyzing these atomic nuclei, the purpose of this experiment is to measure how these atomic nuclei will decay and what mechanisms are involved in nuclear fission. Therefore, it will be possible to investigate nuclei that were not reachable without einsteinium. It is known that a change in the number of neutrons in the atomic nucleus of an element in this series, even by 1, will dramatically change the mechanism of nuclear fission. By combining the unique nuclear fission measurement techniques that JAEA developed ahead of other countries, we are trying to understand the mechanism of this nuclear fission. This apparatus was designed and developed by JAEA to measure nuclear fission. JAEA built this apparatus a few years ago. How does it work? The main tandem accelerator stands on the opposite side of this wall. A heavy ion beam is accelerated and supplied from that side. After passing through this duct, the beam is applied into this spherical chamber, in which an einsteinium target is set up. Then the target is irradiated by a heavy ion beam to cause a nuclear reaction. After the nuclear reaction, the atomic nucleus decays during the process of nuclear fission. The resulting nuclear fission fragments are measured by 4 detectors. The mechanism is set up to work in this round chamber. What are the deliverables resulting from this study? One of the most arguable issues today is that nuclear power generation produces long-life nuclides called minor actinoids. Because of their long life, minor actinoids must be stored for a long period. The knowledge we will obtain from this study and the utilization of data we will accumulate may lead to ideas on how to make minor actinoids decay into non-toxic atomic nuclei. This is the kind of application we are envisioning. Another important facility is the world's largest third-generation synchrotron radiation facility, Spring 8 in Hyogo. This experiment is intended to explain the mechanism of how an einsteinium element and water molecules are bonded in aqueous solutions. In fact, there were a few experiments in the past which used einsteinium, but those experiments were not for chemistry solutions or for the determination of the bonded structure and electronic state. This is why this experiment is called the first of its kind in the world. At the large synchrotron radiation facility, Spring 8, JAEA developed an apparatus that can analyze water molecule coordination around the element using extremely small sample amounts, 0.1 microgram. Using this apparatus, we will obtain data on einsteinium for the first time ever. Because only very small amounts of samples are available, the detection sensitivity of this experiment must be very high. The use of high-intensity radiation from the world's most advanced facility, Spring 8, enabled this experiment. How does the apparatus work? Passing through this slit, a synchrotron radiation beam irradiates the target after passing through the ion chamber and reaches another ion chamber on the other side. This detector is used to measure X-ray scatter to 90 degrees relative to the beam direction. This experiment is conducted using small concentrated sample solutions in the order of 10 ppm. Only this apparatus can conduct this kind of experiment. The analysis of these high concentration samples is only possible through the combination of an intense radiation beam generated by Spring 8 and the use of this detector. This beamline, the ZAFS, is the only one of its kind in the world that can measure X-ray absorption spectra. What do you expect to learn from this experiment? It is relatively easy to understand the behavior of an element series in which electrons are added to the outermost shell, because by making them react with other elements, the characteristics of such elements can be understood. When it comes to elements in these two series, however, electrons are added to the inner shells, and the behavior of such elements cannot be understood by simply making them react with other elements. Among such elements, einsteinium, whose electrons are configured in the inner shell, called f-orbital electrons, is the first to appear on the outer shell. In other words, we can learn the behavior of this element among other elements in these two series. In this sense, we believe this study has profound significance. What are the deliverables resulting from this study? As tangible deliverables, we are interested in the following 2 points. One is lanthanoids, which are located above actinoids in the periodic table. Lanthanoids are elements in which electrons are added to f-orbital. In these elements, electrons are configured in the inner shells, and it is difficult to understand the behavior of the elements by observing the state of f-orbital electrons. Having said that, the use of magnets made of neodymium and dysprosium in this element series are extremely helpful in our daily lives. As I just mentioned, our first point is that the characteristics of such f-orbital electrons are contributing to people's everyday lives. The other point is a problem of high-level radioactive waste from nuclear power called negative legacy, and the phenomenon of meltdown as we saw in the nuclear accident in Fukushima several years ago. We must come up with ideas on how to safely dispose of this waste. The knowledge learned from this experiment with einsteinium is useful in solving such problems. It is very important to produce results that no one has produced before. I am enjoying this work, and I'm proud of it. I am very excited about this experiment, and all our members working on this experiment share the same excitement. No one has conducted this kind of experiment using this element. The involvement in this experiment is a great pleasure for me as a researcher, and this is a moment of intense excitement.